All right, ladies and gentlemen, let's get some more practice in. So this problem is next in your notes. We've got to figure out how to graph this thing. If we try and find intercepts and say 0, or try and find x-intercepts and say 0 is equal to x cubed minus all this stuff, it's not gonna be easy necessarily to try and find a way to do that. So we're not going to worry about it. But if we put a 0 in for x's, 9 times 0 squared plus 24 times 0 minus 10, then we have the point 0, 10, 0, negative 10 as a y-intercept. Okay, so we have the point 0, negative 10. All right, what else can we do? Look for asymptotes. Doesn't look like there's any asymptotes in here. We don't have any value over a denominator that will become undefined. We could check end behavior, though. I mean, I guess we do that towards the end, so we'll do that then. So let's go on to first derivative. First derivative, f prime x is equal to 3x squared minus 18x plus 24. Now let's make that equal to 0 to find critical values. Take out a 3 from everything. X squared minus 6x plus 8. See your factors there. X plus, can be 2 minuses. X minus 2 and x minus 4 equal 0. So we have critical values at 2 and 4. Right? All right, now what do we want to do with those critical values? We could set up to see where the function is increasing and decreasing. If we wanted to, we could do that timeline and put some values in there. We've just been practicing going straight to second derivative, so let's do that next. Second derivative is going to be 6x minus 18. And so if we set this equal to 0, 6x equal to 18, and x is equal to 3. And so we have an inflection point at 3. Now let's test values in the second derivative because we found 2 and 4. We found 2 and 4. So let's put 2 in here and 4 in here in the second derivative and see what values we get. If I put a 2 in there, 6 times 2 minus 18 is going to be a negative 6. And if I put a 4 in there, 6 times 4 is 24 minus 18. It's going to be a positive 6. So we're going to have concave down followed by concave up. That means that if I'm thinking about my faces, 4 is a minimum and 2 is a maximum. Okay, specifically where are they? We could put the values in there, right? We could put 2 into the original function, put 4 into the original function if we wanted to. That takes a calculator to do that, honestly, so that might not be exactly what you want because you might not be allowed to do that, but we'll give them to us. If you plug in 4 to that function, you get 6. So that is going to be a minimum point in our graph. If you plug in 2, you get 10. So 2, 10, that's going to be a maximum on our graph. Okay, then we should test end behavior. So end behavior, what's going to happen when we plug in infinity into this function? So like when the limit of x is approaching positive and negative infinity of this function, I mean, what happens? Well, there's only really one term we really have to be concerned about because all this other stuff pales into comparison as to what happens with that x cubed. When I put a negative infinity into x cubed, it stays negative. And so as I go it just results in negative infinity. And if I put positive infinity in there, cubed, it just results in positive infinity. So what we're saying here is as I go to negative infinity, my graph is going to negative infinity values, like that. And as my graph goes this way, into positive infinity, then my values are going up to positive infinity. So I'm going to have a graph that kind of has this look to it, and that's the cubic equation, right? So let's put it together. So on here, I'm going to have a 2, I'm going to cross at a negative 10. So down here, negative 10 is where I'm going to cross, and then I get to 2, and I find my maximum at positive 10. Wow, way up here. Okay. Then I have a minimum at 4, 6. So right around here at 6, I have a minimum. Now I have to start from negative infinity, go up, cross that. I didn't do the best there. Let's try again. So this is going to be real thin. I have to cross and go way up here. And then where's my inflection point? My inflection point's at 3. Okay. So I have to change from concave up to concave down right about here. Sorry, I'm jumping ahead here. So that final sketch almost done. Just had to wrap up that last swoop. But I do want to get this last problem in. I want to make sure you have enough time to see it. So this next problem is going to have some asymptotes in it. And so we have to consider what kind of asymptotes there are. Now we have asymptotes that are considered horizontal asymptotes and vertical asymptotes. They also can be defined by limits. So horizontal asymptotes travel along the x-axis to positive and negative infinity. So what's happening as my graph goes to positive infinity? What happens when my graph goes to negative infinity? Vertical asymptotes focus on a single point on the x-axis, so a point K. And they say, well, what's happening when I approach K from the right? And what's happening when I approach K from the left? And so the result, after the equal sign, the output can be positive infinity or negative infinity. And you see that here. So that's just a quick rundown of what we've learned about limits before. Now we're going to see them in this problem. Because this problem says to sketch a graph that has a denominator you can cause to go undefined with a value of x. And so we start the same like we do for our other sketches. We say, can we find y-intercepts? Can we find x-intercepts? So if I set this equal to 0, 3x over x plus 2, there are a couple values that we can consider here. The top part we could make 0. If 3 times 0 is put in, I get 0. And so I do have an x-intercept. And that x-intercept is at 0, 0. Right? I also have this bottom though, and when I put a negative 2 in there, when x equals negative 2, it becomes undefined. And so this is typically an asymptote. So we have to look for those asymptotes in this problem. Okay, I'm going to move my screen here a little bit so you can see below me. This is the way we explore a vertical asymptote. We take the value that's undefined, x equals a negative 2, and we consider what's happening to the right and what's happening to the left. See those little symbols we learned with limits? What's happening to the right and to the left of this? And if you recall, these were actually mental math problems where we had to take a value that was slightly above a negative 2, like a negative 1.99999, and put it in for x and consider what happens. If we do that, we get a small positive value on the bottom, right? And I think that's too many zeros, but you get the idea. So that when we put the value in there, the value becomes very big, right? Very big, very quickly. Now the top part actually gets an x as well, which causes this to be negative on top. And so we have a negative over a exploding value on the bottom. It looks like we're approaching negative infinity from the right side. Okay. Over here, we end up, let's put a value in that's slightly below -2, so like a -2.0001. If we do that, we end up with a -0.0001, and on the top, we end up with a negative 6 point something. That's really another value that doesn't matter because we're dividing by a huge one. And so we have negative over negative though. So this ends up being positive infinity when we're done. Okay. Point to whatever. Okay. So this is a look at how vertical asymptotes are found. So our graph has this vertical asymptote at -2. And it looks like as we approach it from the right, we're going to negative infinity. And if we approach it from the left, we're going to positive infinity. That's what it's looking like right now. But we also need to consider horizontal asymptotes. Is there one? We can check by saying what happens when I go to x to infinity and x to negative infinity, because this would be like going way over here on my graph. This would be going way over here on my graph. And see what behavior is happening to the function. This is just like a limit problem. You do it like you would any other problem. If I put infinity in there, I get infinity over infinity. You remember that's indeterminate, so you can take derivative, and that's easy. Derivative of the top is 3, the derivative of the bottom is 1. And so voila, there's your value. The limit as x approaches infinity of this is 3 over 1. Over here, we have the same problem. If we put negative infinity, we have negative infinity over negative infinity. That's indeterminate. So we can think of it as taking derivative. So what's derivative of that? 3. What's derivative of the bottom? 1. So 3 over 1. Looks like we have a horizontal asymptote at 3. So 1, 2, 3 up here. Looks like this graph would be more like this. This graph would be a little more up here. And we have this horizontal asymptote going through. Right? So that's kind of the asymptotes going on in this problem. Can we use anything else to find maximums, minimums, and things like that? So let's check it out. Well, we need derivatives. We're kind of jumping around a little bit, but there's the work for first derivative. Okay, now first derivative over here, after following quotient rule, you have 6 over x plus 2 squared. And the tough part is when you set this equal to 0, like you don't have any critical values. I mean, technically -2 is, but we know that's an asymptote. And so you can test values in the function like -5 and 0. And when you plug those into the first derivative, you find out it's increasing the entire time, which is pretty crazy, right? So maybe second derivative will tell us something. We can at least find concavity. We can determine if there's maximums or minimums at that point. So here is first derivative. Change it a little bit and go to second derivative right here. Okay, second derivative, bring down the -2, follow chain rule, and then simplified is 0 equals the -12 over x plus 2 cubed. But this is another bizarre function because you don't really have much going on there for inflection points. You can test values around it and plug in values like a -5 and 0 again, and you end up with a negative and a negative on the bottom here. So you're concave up there, I think. And if you put 0 in, you end up with a negative, so you're concave down. So there's some, you can get some concavity in here, just like you can get increasing and decreasing. But now it's time to kind of put this function together, and you've got some weird stuff going on. I mean, this is really what we've found. Okay, and so how do you put a graph like this together? Well, going back to our graph that we did before, we said it has a horizontal asymptote at 3, it has a vertical asymptote at -2. So we're looking at always increasing, and so I'm thinking something like this, always increasing, concave up, concave down. And we've got a boomerang function. And there you go. There we are. So there's a bizarre one, but that's you just follow what you get. And there you have it.